So now that we've learned all about finite state machines, it's time to start applying these to real-world applications. So we're going to start here with this example on a plant watering controller system. And I'm going to walk you through the process of how to go about designing these state diagrams. So we're going to generate a state diagram that could be used by a finite state machine to control a plant watering device. This device has two outputs. One output, dry, indicates when the plant medium is in need of water. The other output, flood, indicates when the water level has reached a given point. The watering device has one input, water, that controls whether water is pumped into the planter or not, and the operation of this device is such that if the planter is dry, the pump actuates until a flooded condition is present. Okay, so how you approach these problems is you first need to read this description and read it again and again to try to understand what is this thing asking. Okay, so in my own words, I'm understanding that I need to be able to turn on water to my plant when it says it's dry and turn off the water when it says I've filled it up with enough water. Okay, so I understand what I need to try to do. The next step, so step 1 is understand the problem. Step 2 is draw a black box diagram that shows how your controller is going to interface with your device. Sometimes you just have to draw the black box of the controller itself. Anyway, here you can see on this page we have our finite state machine, which has one output, water, which is going to control the valve of turning on water to water our plant. And that goes to our watering device, and the watering device feeds back two inputs to the FSM, dry and flood. Dry is coming probably from a sensor that's sensing that this plant is dry, so it sends a signal to the FSM, and flood is that signal sensing that the water has been filled to the appropriate level and telling the FSM, okay, stop giving me water. Okay, so we've drawn now our black box diagram. That was step 2. Step 3 is to draw a legend for our circuit. So I'm going to go ahead and design a Moore circuit because I find designing Moores just to be more intuitive. Sometimes Mealy's might make more sense, so you just need to decide what works for you. So I know that I'm going to have an output, water, and two inputs, dry and flood, and I'm going to have a bunch of states. So I'm going to start by drawing a legend. So here we go. We're going to draw a legend. It's going to be a bubble. I'm going to have some kind of state. I should have drawn a bigger bubble. I'm going to have an output called water. I'm just going to abbreviate it with a W, and I'm going to have two inputs. I'm going to have my dry, which I'm going to abbreviate with a D, and my flood, which I'm going to abbreviate with an F. Alright, so that was step 3. Step 1, understand. Step 2, draw the black box diagram. Step 3, draw the legend. Step 4 is draw the first state. And typically you want to think about the first state you draw as the do-nothing state, or rather you're just kind of sitting there idle, waiting for something to happen. So you could call it the idle state, the do-nothing state, the most boring state. So, okay, so the most boring state is we're just sitting around waiting to water the device. So I'm going to draw a bubble here. I'm going to call this idle. And in this state, I'm not watering. So I'm going to put water not. And I'm not watering so long as I'm not dry. So I just called it D. I was going to write DRY, but I'm just going to call it D. So I'm going to sit in here so long as I'm not dry. Now, what if I get the dry input? Dry means I better start watering, right? So I'm going to move to the next state. I'm going to call this state the water state. And in my water state, that means I want to actually give this thing water. So in my water state, that's because I got the dry signal, so D caused me to move to the water state, which will turn on the water, and I want to have the water on so long as I'm not flooded. So I'm going to say, so long as I have a no flood input, I'm going to keep watering. Once I get the flood signal, then I want to stop watering, so I want to go back to the idle state. Okay. So this actually does everything we wanted this circuit to do, that I'm going to hang out and not water so long as I'm not dry, and then once I'm dry, I better start watering and keep watering until I'm flooded. And there you go. That's exactly what this control system was supposed to do. Now, it's important to note that whenever you have outputs coming out of a state, you need to take care of all cases. So, in this case, we have two inputs, so we should take care of all input cases for all states. So in this case, in our idle state, we have a D naught and a D. Now what about F? Well, actually, we don't care what F is in this state because there's no way we would get a flood signal or not flood signal. We don't care what it is because we're not watering anything, so there's no way that the water level could be rising since we're not turning on the water. This is, of course, assuming there's no rain, which is going to maybe affect your level. But anyway, picture this as an indoor plant. So the F is a don't care, therefore we've taken care of all possible input combinations because we're only going to care about D, and we said what would happen if D is a not or D is a 0 or D is a 1. Similarly, in the watering state, we don't care if we're getting a dry signal because there's no way that if we're watering the system we're going to be getting a dry signal because guess what? There's water, it's wet. We don't care what D is. So we've taken care of every possible input combination because we have an F naught and an F coming out of the water state. Alright, so there's a first example of applying a finite state machine to a real-world problem. Now we're going to, in the next video, look at how to make a more complicated watering device.